Alright, good morning, good afternoon, good evening classes, Mr. Arocena, and on today's video we're going to be talking about how to calculate electric power and what EMF is. Alright, so first electric power. This is similar to power from previous units that we've talked about. If you recall, power is really the amount of work done per second, or how much energy changes per second. So it's just a way of describing energy per second. Now, in terms of electricity, anytime you have electric current, every electric current will generate some amount of heat, because when current passes through a substance, the resistance that the current or that the substance has will cause the electrons to generate some heat. Now, it turns out that the heat generated per second, otherwise known as power, is proportional to the square of the current. So power, electrical power, depends on how much current is passing through the substance squared. And during a study of energy, Joule actually realized that this constant is actually another part of the circuit. So I is current. So yeah, Joule, during his study of energy, realized that the K in this particular relationship, the proportionality constant, is actually just the resistance of the current, or resistance of the resistor. So for electricity, for electric currents, power is really the product of the resistance and the current squared. So the more resistance you have, the more heat you can generate. And this is generally speaking heat generated, heat energy generated per second is dependent on the resistance of the circuit and how much current is flowing through it. And this is kind of how a lot of electrical heaters are created. They basically have a substance with a relatively high resistance, and then they just pass a current through it, and that will cause the substance to heat up. It'll generate heat energy, and then that can be transferred to the environment. So like stovetop elements work that way. Toaster oven elements work that way. If you have an electric oven, the elements in your electric oven work that way. Even portable heaters work this way. Now, we'll revisit electrical energy, and we generally measure this in joules. So if you remember when we were talking about electric potential energy, we'd measure the energy in joules. Now, the joule, however, is is too small a value when dealing with large-scale usage. For small-scale usage, we use the electron volt, but for large-scale usage, we actually use a different unit, which we call the kilowatt hour. Basically, this is the amount of energy used. So, amount of energy used by 1 kilowatt of electricity or of electric power in 1 hour. And you can sort of calculate the joule equivalent as 1000 watts times 3600 seconds. And I think this will end up being something like 3.6 times 10 to the 6 joules of energy. So this is what we would use for measuring the amount of energy, like say a house or a building uses. The joule is just too small a value because we're talking about, in general, millions of joules of energy being used on a large scale. There you go. So that's a quick overview of electrical power and another unit for measuring electrical energy. Now let's go through some examples of calculating using these equations. All right, so for example, we're asked to calculate what's the power rating of a kettle if it has a resistance of 9.6 ohms and 12.5 amps of current flows through it. So our equation is the power is equal to the resistance times the current squared. Our resistance is 9.6 ohms. We have a current of 12.5 amps flowing through it, and that'll be squared. So our total power, 9.6 times 12.5 squared. So this kettle will have a power rating of 1,500 watts. 100% efficiency, this will deliver 1,500 joules of heat energy for every second it is operated. Another way you can sort of view it also is that this is how much energy it's going to use up, or it can transfer per second. All right, example 2. We'll take our kettle, so our 1,500 watt kettle, and we're going to calculate how much energy it can release in 5 minutes. We'll convert this energy to kilowatt hours, and then we'll calculate how much it costs to operate this kettle if the current rate of electricity is 6.67 cents per kilowatt hour. All right, so the amount of energy, if you remember, power is energy per time. So we have our 1,500 watt kettle, that's its power rating. We want to figure out the amount of energy it uses or creates, and we are operating at 5 minutes. We'll convert that to seconds, and then we just carry out this calculation. So this will be 1,500 watts times 5 times 60 equals the amount of energy. So 1,500 times 5 times 60. So this will generate 450,000 joules of energy. 450,000 joules of energy. Okay. Then we'll convert this to kilowatt hours. So 1 kilowatt hour is 3.6 times 10 to the 6 joules. So if we want to do our conversion, we'll just take our, I guess we'll do this, x kilowatt hours over 1 kilowatt hour is equal to 450,000 joules over 3.6 times 10 to the 6 joules. We can cross multiply, divide, and we get the following. So 450,000 divided by 0.6 times 10 to the 6. So total kilowatt hours, 0.125 kilowatt hours. And finally, I'll calculate the cost. So the cost will be 6.67 cents times our 0.125 kilowatt hours. So to operate this kettle for 5 minutes, it will cost us less than a penny, 0.834 cents to operate. So operating a kettle is actually quite cheap, doesn't require too much money to operate this kettle. So the kettle is obviously not the most expensive appliance to operate. You can perform similar sets of calculations to figure out the cost of other appliances. So for example, like a washing machine or a dryer or a dishwasher and so on. Right. Now, as far as electricity goes, we use a lot of batteries, and batteries have a interesting property, or I guess not property. We have another definition for the voltage of a battery, that's called EMF. And all batteries have this property called EMF. EMF is short for electromotive force. Electromotive force. And the EMF is the ideal voltage of a power source. So this is the, you create a power source, its EMF is what you expect or what you design it to create, the amount of voltage it creates. Now, because because you can't actually get a substance with zero resistance unless it's a superconductor, every battery, every source of power actually has what's known as a terminal voltage. And terminal voltage is the actual voltage you get from the power supply after you take internal resistance into account. Now, internal resistance is basically the resistance caused by the substance itself. So if you have a battery, the battery will actually resist itself because it's just the nature of the way it's constructed. It's not entirely resistance free. So to calculate terminal voltage, we use this equation where this symbol here is our EMF. So that's the ideal voltage of our battery. So if you had like a 1.5 volt battery, its EMF would be 1.5 volts, or in other words, its ideal voltage would be 1.5 volts. But it does have some kind of internal resistance, and its actual voltage, so this is the voltage that the useful voltage you actually get, is determined by this calculation here. Now this this will be the current in the battery. The current in the battery can be determined by doing some circuit analysis. We'll get to circuit analysis in the next lesson. Example 3 then. We're given a battery and it has an EMF of 1.5 volts. So this would be like a standard 1.5 volt battery. It's rated at 1.5 volts. It has a small internal resistance of 0.05 ohms, and we're asked to find what is the terminal voltage if we connect it to a 2 ohm resistor. Alright, so I'm just going to draw this out. So there's my battery. We are connecting it to a 2 ohm resistor. Although I'm going to add the battery's internal resistance here as a smaller resistor like that. So there's our small resistance, here's our large resistance. Then we're asked to find what is the terminal voltage if it is connected to that resistor. Okay, so terminal voltage is EMF minus I times R. Alright, now in this particular question, we don't actually know what the current is, but we can figure that out using Ohm's law. If you remember, Ohm's law is V equals IR. So so the voltage is equivalent to the current times the resistance. Now here we have two resistors which are connected together. So since they are connected together like that, we can actually add up their total resistance. So from Ohm's law, we can then say V equals I, and the total resistance of this simple circuit is R plus R. We'll get into some more, we'll get into what to do if the circuit is constructed differently in the next lesson. But for now, if you have two resistors back to back like this, you can add up the resistances to get the total resistance. So going on, the battery has a voltage of 1.5 volts. Calculate the current. Its total resistance is 2.05 ohms. So from here, you can calculate the current flowing through this battery and by extension the circuit with that equation. 1.5 divided by 2.05. We have a current of 0.732 amps. And now we can take this current and put it into here to figure out what the terminal voltage of the battery is. Terminal voltage of the battery, the EMF, which is 1.5 volts. We have a current of 0.732 amps, and our resistance is 0.05 ohms. Our total terminal voltage, 5 minus 0.732 times 0.05. So our battery can provide 1.46 volts of actual voltage to the rest of the circuit. And that's what terminal voltage really means. This is the voltage available to the rest of the circuit. So if you had a device that needed exactly 1.5 volts, this battery would not be able to provide it because its terminal voltage is actually less than that. Usually most devices will still operate with a lower voltage, just won't operate at peak efficiency. So if you had a light bulb that needed 1.5 volts of potential difference, then if it's only getting this much, it might not shine as brightly. And all batteries exhibit this because every battery has a small amount of internal resistance. We try to limit that as much as possible so that the terminal voltage of the battery is equal to its EMF, but we can't avoid it entirely. All right, so there's some quick examples of how to deal with electrical power and a quick definition on EMF and terminal voltage. As far as circuits go, we'll get into some more circuit-heavy things starting with our next lesson. Right, so your assignment then for this to just practice some more calculations is as follows. If you have any questions, you guys all know how to contact me.